Alright, so now we are taking our work with springs to other planets. But for our simulation, we're still going to be in this lab part of it, so I'm going to go ahead and click there. The settings are largely going to be similar to what we were working with before. I'm still going to set this damping to none. I still want to check all of these boxes. That'll be useful information to us later. We're going to stick with the 100-gram mass, and I'm going to change this to the 5th notch spring. And the reason for that is that we are now increasing the gravity as we take this spring and mass system to Jupiter, where our gravity is 24.8 meters per second squared. And when I attach this mass, so 100 grams, you'll notice it bounce. I'm going to go ahead and pause this so that it's easier for me to drag that mass around. I'm going to pull out this ruler because I have to drag this mass to a certain displacement. In your work for the Thursday and Friday stuff that is here, I ask you to drag it down to a 75 centimeter displacement. As a reminder, that displacement, you need to make sure you have the top of your meter stick lined up with that mass equilibrium, or excuse me, with the natural length, so that blue line up there. And then we measure this green vector going down, so I need to make sure that I drag this a little bit farther so that it gets all the way down to that 75 centimeter mark, as long as I have my meter stick lined up correctly. And so now, what I ask you to do here is very similar to what you all did this past Monday, where you had to calculate the gravitational potential energy, the kinetic energy, and the elastic potential energy. And then eventually you'll have to calculate the mechanical energy, which is the sum of all of those. So you'll add all of those up. The only thing to really keep in mind as you do this work now on another planet with different gravity is that in our gravitational potential energy, the G that you're going to use now that we're on Jupiter, is not going to be 9.8 anymore. Now it's going to be that 24.8 meters per second squared. But our equations for kinetic energy do not change. 1/2 mv squared still. And this elastic potential energy also does not change, at least in its form. It's still 1/2 times k times x squared, where k is our spring constant, x is the displacement shown by this green vector in our simulation. So I'm not going to go over in this video how to calculate that kinetic energy or the elastic potential energy. We've sort of talked about those things ad nauseum to this point. If you need some review on that, I'd recommend going back to the Monday video where I go over sort of how to calculate both of those different types of energies. But as an example for this gravitational potential energy, I'll go over that. Now in your all work, you're going to have to drag this to this 75 centimeter displacement that I have here, just as an example so that I'm not giving answers away. I'm going to drag this to a different displacement. Let's say it is to 60 centimeters. And now to measure my height, so that 60 centimeters is just the length of this green vector for displacement. But when I measure the height to be plugged into this gravitational potential energy equation, I need to line up the meter stick so that it is in line with this height equals 0, the ground. I'm moving the movable line, the red line in the simulation, to the middle of the mass because we have to measure to the center of mass in the simulation. And it looks to me like this comes up right to about the 70 centimeter line on our meter stick. And for me to record that height then, I need to take this 100 centimeters that's on the ground right now and subtract the 70 centimeters that it moves up to. So I'm recording this as 100 because that's what's on the ground, and then subtract whatever we get up to on this meter stick since it's all upside down. And so the height here is 30 centimeters. And so that is then what I'm going to plug into our equation. So for the mass, I know that 100 grams is the same as 0.1 kilograms. I know that the gravity now is not 9.8 anymore. Remember, we're on Jupiter. So now our gravity is 24.8 meters per second squared, and I'm multiplying by this 0.3 meter height. And we just multiply everything straight across. 0.1 times 24.8 times 0.3. And I got a gravitational potential energy of about 0.74. The exact answer was 0.744. I'm just going to record 0.74. I'll stick with my sort of 2 decimal rule that I've been putting in all the work. So again, that's how you calculate gravitational potential energy. Make sure you're careful still with how you measure height. And then when you're plugging into this familiar equation, make sure you're using the correct gravity for the planet that we're on now.